So let's move on and now understand stator and rotor topologies. So what is the meaning of a topology? Topology means the configuration, the type, or it can be also simplified as how they are created. So what is the style of stator and the rotor? And actually there are many style, or there are many types exist. Let's try to see the rotor types. Rotor magnetic poles, their type and the number of pole pairs are decided based on the type of the magnetic material and the overall requirement of the magnetic field in the motor. So there are two types of rotor, as we have seen in the previous slide: outer rotor and inner rotor. And outer rotor and inner rotor are classification of the motor according to the rotor. Basically the outer rotor motor are something similar to a ceiling fan motor or the hard drive motor, which we have seen earlier. And most of the types of motor are inner rotor, where the stator is basically surrounding the rotor. So if I draw the red part as a stator, and if I have a blue color for a rotor, this is basically the inner rotor configuration. And most of the type of motor are this configuration. The rotor is inside the stator, but the reverse is also true, where the rotor is outside and the stator is inside. So if you consider a ceiling fan motor, basically the ceiling fan motor is of single phase induction motor type, and that is outer rotor motor. So where the center of the stator is fixed to the ceiling, and the periphery of this red color stator consists of split phase winding, and the rotor is basically the blue colored part, and it is connected with the wings, and when the rotor rotates, the wings will also rotate. The outer rotor motor is also popular for electric vehicle application, as we have seen, and this can be directly connected with the wheels. So let's see more types of motor according to the orientation of the magnets. According to the style in which the magnets are inserted into the rotor, there are mainly two types: surface permanent magnet or interior permanent magnet. So here is the difference between surface and interior permanent magnet. So the permanent magnets which are on the outer surface of the rotor, they are called surface permanent magnet. So this is one important classification of different types of PM rotors, whether it's surface permanent magnet or interior permanent magnet. So the interior permanent magnet motor is offering more advantages over here because it is well embraced into the rotor core, and the arrangement of the permanent magnets, or we can say the flux available from this permanent magnet, is going to be more effective than the case of a surface permanent magnet. And also because the rotor is rotating, the centrifugal force will be experienced by this permanent magnet material, and that is also the reason where in case of a high-speed drive, the interior permanent magnet can be more preferable. So here the utilization of the core material in this case and this case, it is better for the interior permanent magnet motor. So let's move ahead and now see another difference of axial flux and radial flux machine. So basically we are not going to see the axial flux machine, we will be only focusing on radial flux machine. So what is the difference? This difference is based on the direction of useful flux. So if the direction of the useful flux is radial, or we can say perpendicular to the shaft of the machine, then it is radial flux, and normally it has large length compared to the diameter. So most of the motors which are of this type, where its length is larger than the diameter, then these type of motors are radial flux motors. And axial flux motor is basically compact and sandwich type construction, and their diameter is large but length is small. So if I draw this kind of a motor, it will be something similar to this, where its length is quite small, and this can be another arrangement of, let's say there are two rotors and there is a single stator in between. So radial flux and axial flux machine are another classification based on the direction of the flux, and there are other types of machine also possible, which are called transverse flux machine and linear flux machines, which we have seen in the classification of motors. So if I give you a diagram of a radial flux and axial flux machine, it will be look like something this. So here you have the outer rotor and the inner stator, and basically the stator is having windings. So here you can see the winding parts, and all these windings are kept on the stator, and the rotor is consisting of two permanent magnet poles. So this is a simple construction of a radial flux machine. So the direction of the flux is something which is given as this dotted line. So this black dotted line starting from N pole to S pole basically figures out the radial flux machine. Over here the axial flux machine is something different, and the direction of the flux is something which is indicated by this dotted lines. So here what you see is the direction of the magnetic field, and that is going to pass through the stator part, and therefore this will be the rotor, and the other part where the windings are mounted, it's a stator, and the direction of the flux is in the same direction of the shaft, and therefore it's called the axial flux. Here the direction of the flux is actually perpendicular to the shaft, and it's a radial flux machine. So this is an important difference to be understood for motor design. Let's now move ahead and look into the design for the stator. So how do we choose the stator number of slots and winding topology? So the number of stator slots and the configuration of the winding is very important. Now the three-phase winding for a motor can be configured in many different ways. It can be connected in star or delta, which is the most simple connection, but there are other ways of connecting a winding as well. So for stator number of slots, there are certain rules which are followed such that this stator number of slots will be a valid number. So what are these rules? Let's see those rules. So the first is number of slots per pole pair should be always greater than 1. So per pole pair, whatever are the number of slots, that should be greater than 1. And this ratio, or we can say the slots per pole pair, is always higher. So here you have more number of slots than pole pair. So why is it required? Because usually the magnetic poles will be generating much more magnetic effect than the conductors which are there inside the slot. So there may be number of parallel paths in a winding, there may be number of multiple conductors in a slot, and the magnetic effect generated by those ampere turns, which is required to be higher than the effect of the poles. So the second rule is slots per phase per parallel path should be an integer number. So if you are choosing the number of slots and you have 3 number of phases for the motor, then number of parallel paths and the slots should be chosen in such a way that it is resulting into an integer number. It should not be a fractional number. The third rule is number of pole pairs divided by parallel path should be equal to an even number. So 2 times k, where k is an integer, and basically the rule stands here, this should be an even number. So parallel paths should be always equivalent to the number of pole pairs times 2k. So this is the third rule, and pole pairs per parallel path should be an even number. The last rule is number of slots per phase per greatest common divisor of slots and the phase should be equal to an integer number. So here we take gross common divisor GCD of the values of slots and the phase, and that should be equal to an integer number. It should not be equal to floating point number or a non-integer value. So now let's move and let's discuss about why do we need a computer simulation for a motor design. So as we know, there are many different types of shape, geometry and material, and solving the electromagnetic equation is basically required to calculate the torque developed by the machine. So in order to estimate the torque which is developed by the machine with a given excitation, you need to solve the fundamental electromagnetic equations. So this fundamental electromagnetic equation are known as the Maxwell's equations. So basically the computer simulation tool will be solving Maxwell's equation, and it's always better to simulate and virtually test the motor before manufacturing. So the computer simulation for a motor design is very much required in order to virtually test the machine before actually making a prototype or going for the manufacturing. So what is this? What are the steps? So the steps are like this, where you have an electrical circuit, and from the simple electrical circuit you develop electromagnetic arrangement, or we can say the electromagnetic equations. Now those electromagnetic equations will be producing the mechanical forces, and due to the losses of the machine there may be certain thermal effects. So these are the fields of interest, right? So the motor design is not a single activity where you deal with only electrical circuits, where you have resistor, capacitor, inductor and a source or excitation, but it is also related to electromagnetics. It's also related to mechanical forces which are developed, and ultimately none of the motor is going to be perfect, right, or 100% efficient. So each motor is going to have some kind of losses which will result into temperature rise, and this different field of study, electrostatic, electromagnetic, mechanical and thermal, basically requires a multi-physics approach for a motor design, and therefore the finite element analysis is one of the method which is preferred for computer simulation. We are not going into detail of finite element analysis, but how it works, basically it divides the geometry into fine number of meshes, and it solves the equations for various different types of meshes. When the equations are solved for all the meshes, you have all the performance data for the given geometry. So the finite element analysis and solution of the Maxwell's equation, and these are the complex tasks required for a motor design exercise, and therefore there is a powerful computational requirement and powerful software tool is required for the motor design. So let's now move on and let's go to the Ansys RM Expert based motor design. Before we jump into the Ansys tool, let me explain you what is RM Expert. So RM Expert is basically rotating machine expert tool, and it is based on template. So the template are already available in this tool to quickly configure your motor design case. Now, what is a template? So if you remember our analogy to the motor, where there are various types of footwear for human being, right? Similarly, there are many types of motor for different applications. So if I give you an idea about how a shoemaker is going to make the shoes, so shoemaker might have some idea about the dimension and the size and the shape of a leg, right, for which he is going to design the shoes for. Similarly, if you have the fundamental idea of your motor design, you can jumpstart your design with the template based design tool. So this is going to create simple template like this shoe mold. So a shoemaker normally uses this kind of wooden mold for making a shoe, and this is basically a template, and based on this template the shoemaker is going to quickly configure the material around this and make the shoes ready quickly. So similarly, the Ansys RM Expert is also the tool which will configure your motor quickly. So let's see Ansys RM Expert first.